Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of engineering chemistry. We'll dive into key concepts like mechanism of polymerization, free radical, and ionic polymerization, thermoplastic and thermosetting polymers. Slide 1, Mechanism of polymerization, Introduction. 1. Definition of polymerization. Polymerization is the chemical process where monomers, which are small, repeating units, combine to form large, long-chain molecules called polymers. Example, ethylene, CTWOH4, molecules can polymerize to form polyethylene, a common plastic. 2. Types of polymerization mechanisms. There are two primary types of polymerization mechanisms: free radical polymerization and ionic polymerization. Both involve the growth of polymer chains, but differ in the initiating species, radicals in one and ions in the other. 3. Importance of polymerization. Polymerization is significant because it enables the creation of materials with specific properties like strength, flexibility, and chemical resistance, essential for various engineering and industrial applications. 4. Applications of polymers. Polymers are extensively used in plastic manufacturing, synthetic fibers, rubber production, and adhesives. 5. Monomer. A monomer is a single molecule unit that can join with other similar molecules to form a polymer. Example, styrene, CH, is a monomer that polymerizes to form polystyrene. 6. Initiator. An initiator is a substance that starts the polymerization process by producing free radicals or ions. Example, benzoyl peroxide decomposes to generate free radicals, initiating free radical polymerization. 7. Propagation and termination. Propagation, the stage where monomers continuously add to the growing polymer chain. Termination, the stage where the chain growth stops, often by combining two free radicals or by disproportionation, where one radical transfers a hydrogen to another. Slide 2. Free radical polymerization. 1. Definition. Free radical polymerization involves the use of free radicals to initiate and propagate the polymer chain. Example, polyethylene is formed through the polymerization of ethylene using free radicals. 2. Initiation stage. In this stage, the initiator decomposes to form free radicals. Example, benzoyl peroxide breaks down to generate phenyl radicals. 3. Propagation stage. The active radical reacts with a monomer to form a longer chain radical. This chain continues to grow as more monomers add to the chain end. 4. Termination stage. The polymer chain terminates when two radicals combine or when one radical transfers hydrogen to another. Example, in polyethylene synthesis, two growing chains can combine to form a single polymer molecule. 5. Example of free radical polymerization. Ethylene plus free radical right-pointing arrow polyethylene, CTWOH4N. 6. Significance. Free radical polymerization is widely used in the production of plastic containers, films, and synthetic rubber. 7. Advantages. Fast reaction rates, simple mechanism, and cost-effective production of polymers. Slide 3. Ionic polymerization, cationic and anionic. 1. Definition. Ionic polymerization uses ions, cations or anions, as initiating species instead of free radicals. It is more controlled than free radical polymerization and suitable for making specific polymers. 2. Cationic polymerization. Initiated by positively charged ions, cations, such as H or Bf. Example, polyisobutylene is produced using cationic polymerization. 3. Anionic polymerization. Initiated by negatively charged ions, anions, like Nun2 or Bali. Example, polystyrene is formed through anionic polymerization using butyllithium. 4. Initiators. Cationic, Bf3H2SO4. Anionic, Nun2N-bully. 5. Propagation stage. Monomers add to the growing polymer chain by ionic addition, maintaining charge throughout. 6. Termination stage. The reaction terminates when the ionic charge is neutralized by addition of a terminating agent. 7. Applications. Cationic, adhesives, rubber products, resins. Anionic, elastomers, synthetic rubber, plastics. Slide 4. Thermoplastic versus thermosetting polymers. 1. Definition. Thermoplastics, polymers that soften upon heating and can be remolded repeatedly. Thermosetting polymers, polymers that harden permanently after initial heating and cannot be reshaped. 2. Structure. Thermoplastics, linear or slightly branched chains, allowing flexibility. Thermosetting, cross-linked, rigid structure, providing strength. 3. Reusability. Thermoplastics, recyclable and reusable after melting. Thermosetting, not recyclable, permanently set after curing. 4. Examples. Thermoplastics, polyethylene, PVC, nylon. Thermosetting, bakelite, epoxy resin. 5. Strength and durability. Thermoplastics, less strong but more flexible. Thermosetting, highly strong and durable. 6. Applications. Thermoplastics, packaging, toys, bottles. Thermosetting, electrical insulators, car parts, kitchenware. 7. Cost. Thermoplastics are generally less expensive, whereas thermosetting polymers are more costly due to cross-linking. Slide 5. Advantages and disadvantages of thermoplastics and thermosetting polymers. 1. Advantages of thermoplastics. Recyclable, can be reheated and reshaped. Cost-effective, economical for mass production. Lightweight, suitable for transportation. Malleable, easily molded into complex shapes. Good insulator, effective for electrical insulation. Transparency, allows optical clarity for certain products. Chemical resistance, resistant to various chemicals. 2. Disadvantages of thermoplastics. Low heat resistance, prone to deformation under heat. Less rigid, not ideal for high-strength applications. Environmental concerns, potential for plastic waste accumulation. 3. Advantages of thermosetting polymers. High thermal stability, can withstand extreme temperatures. High strength, excellent structural integrity. Durability, long-lasting, with high resistance to wear. Chemical resistance, resistant to solvents and acids. Electrical insulation, ideal for electrical components. Scratch resistance, hard surface prevents damage. Stable, retains shape under stress. 4. Disadvantages of thermosetting polymers. Non-recyclable, cannot be reshaped once set. Brittle, may crack under heavy impact. Expensive, higher production costs.